I just want to welcome everyone. This is Mass AITC's monthly webinar series, and we're really privileged today to highlight two Grant Year 1 pilot awardees in the space of cardiovascular health monitoring that are really taking some advances in repurposing sort of smartphones and sort of earbud-based technologies, I think earables that people will be familiar with, to advance at-home monitoring, in particular the focus on older adults, but is more broadly applicable to the general population. But our center here is very much focused on healthy aging. And so I'm going to turn it over to Julie Laufenberger, who's an associate professor of medicine at Brigham and Women's Hospital, and is also a member of our Healthy Aging Pilot Corps, to introduce today's speakers. Thank you, Julie.
Great. Yeah, thanks so much for being here today. These two talks are, as David was getting at, loosely related to cardiovascular health monitoring, and both are completed year 1 pilots that we're excited to showcase. And so what we're going to do is we're going to start with one from Anna Bernacca and her on behalf of her team. And we'll go ahead and take her presentation and then take a couple of questions, and then we'll move on to Ed's presentation after that. Take a couple questions related to that, and if there's any extra time, we'll take sort of more general questions. Great. So with that, I'm going to introduce our first speaker today, Anna Bernacca, who's the founder and CEO of Mind Mics, which is a health monitoring company. And what's kind of interesting about the work that she and her team have been doing is really focused on kind of different types of hemodynamics and thinking about cardiac health. And so I'm excited to turn it over to her to present the work that she's been doing under her funded Mass AITC work.
Hello, everyone. It's a great pleasure to be able to show the work we've been doing thanks to the program, and tell you also a little bit more about Mind Mics technology. So Mind Mics technology started with the discovery that actually our ear canal not only works as a microphone and that allows our brain to get the sound from outside, but also simultaneously works as a speaker. And our ear literally is broadcasting every heartbeat, which we can capture using earbuds. And actually today, an earbud with the noise cancellation will have a microphone that is facing the ear canal, and using that microphone that is today used for the noise cancellation, we can actually capture every heartbeat with absolutely superior accuracy in terms of as a wearable device. And in this study, we wanted to push our work further, and we wanted to understand the vascular aging. And especially we know that as we age, and the arteries, the pressure waves, the waveforms, the hemodynamics is changing as well. And seeing the initial data that we're gathering from Scripps Health, we wanted to see how we can quantify it and build the features that in the future could also help us build the algorithms toward the arterial stiffness, and also gives people a way to look at their vascular age as a part of our user experience as well. And also we ask ourselves a question: can we impact our vascular aging with a breathwork? And I will show you what we've been doing and also how much we have learned thanks to that study. So this is the objective of the project was twofold. One thing was we already had initial data that we were collecting at Scripps Health, looking simultaneously through the ear and comparing the data using cardiac catheterization and echocardiogram. So we wanted to quantify those waveforms and see at the different features how we can decompose those waveforms. Because as you can see on this figure in the right, the waveform, the shape of every heartbeat is changing drastically as we age. Usually, actually, the heart, I'm an astrophysicist, so I have learned so much about heart, especially I like to think about heart as a pump, and actually two pumps. One is the vascular, the heart muscle that is contracting, but there is also a second pump that is the aorta. And as we age, the stiffness of the aorta is changing to the point that when it is losing that elasticity, it cannot work as that balloon anymore, so it cannot store that energy of the blood, which means that the blood will travel faster And as the velocity of the blood is proportional to the pressure, also the pressure will increase. So the loss of that stiffness of the, or increased stiffness of the aorta as we age is leading at the end to increase the blood pressure in the older population. So we wanted to understand that relation and how well we can decompose those two components, the one component, those components of the heartbeat of the pressure wave, into the first part, the forward moving wave, and also the reflected one, because they carry different information about the part of the vascular system. Especially the reflected one carries the information about also the vascular aging, and especially looking at the blood pressure as well in those patients. And can we actually have an impact into lowering the blood pressure using the things that everybody can do at not extra cost, which is just slowing down our breathing with the techniques called resonant breathing, for example, which is fancy word for slowing down the inhale and exhale. And for that, we had the chance to actually do the clinical study where we were collecting the data, and I will also show you the results around this. So a little bit before we jump into the data, I wanted to highlight MindMax technology a little bit. So first of all, because we're using the ear canal as a speaker, so what we're detecting is we're using the sound waves. So that's big difference with what is used today in the wearables. Wearables today are using the optical sensor, which is quite bulky, and it's only measuring the blood flow just below the skin. We're not using the optical sensors, we're using the microphones that are in the earbuds. A lot of earbuds will already have the right microphone in the right place for the noise cancellation purposes. So we don't have to even actually add the cost in terms of the earbud build, which is also very important to be able to provide such a solution. On top of that, yes, you can listen to music at the same time, because the frequencies that we're capturing using MindMax are below 20 hertz. So they are below our hearing range. So actually the reason why we don't hear anything below 20 hertz is because actually our body is so loud that the brain had to learn to filter it out. But at the same time, you can listen to music, and MindMax can capture the heartbeats simultaneously. And because we have no extra sensor, no extra battery drain, plus also sound travels irrespective of the skin tone, and we get gathering completely new level of insights in terms of the quality of the waveforms and quality of the heartbeats. So the first part of the project was to look at the data that we just gathered at Scripps for different patients, and we simultaneously had echocardiograms. So here I'm showing the examples for 4 participants of that study. And on top you can see echocardiogram with the blood flow in average. Here we were using about 3 heartbeats. And what's really interesting is now when you look at the second into those blue lines, this is the blood pressure in the aorta for a few heartbeats. And below, simultaneously, those are the data that we collected with MindMax simultaneously through the ear. So actually what is very striking, even though already you can see the differences in the waveform across the patients, MindMax keeps a very high correlation. The waveforms from MindMax, the yellow ones, they are very similar in the shape to the waveforms captured using very invasive procedures like cardiac catheterization. So that was already very encouraging. And also just to tell you what else we have on this plot, when we're looking at MindMax, when we're looking at the signal below 20 hertz, between 1 and 20 hertz, what we see is something very similar to what we detect with the cardiac catheterization, which is the pulse wave. But also with MindMax, when you look at the waveforms, you will see that there is a lot of smaller wiggles as well. Those smaller wiggles, it's also when we look at the frequencies about 20 hertz through the ear, we can also detect the heart sounds as well. So this is not that much related to the study we've been doing around the vascular aging, but still very interesting parameter about our cardiac health, as we can see the heart sounds and murmurs as well. And at the bottom, you can see the ECG. So just you can see the timing of those waveforms, that also how well it aligns. So we actually can see a central part of the cardiovascular system in real time with article of opening, blood flowing and artery valve closing, and then diastole part as well. So we, in the first part of the project, we took all of those waveforms, and simultaneously we were using the waveforms from the cardiac catheterization and from MindMakes, and we've been developing few methods to decompose those waveforms into multiple parameters. So here I'm just only highlighting one of them, where we were using few Gaussians to decompose the pulse wave. We also were looking at the different method, like looking at the reservoir of the blood as well. So that was the first part of our study, which allowed us to build a lot of features that we could compare the either quality between the cardiac catheter and also MindMakes in the ear. And also it allows us to really look at much bigger data set and combine those waveforms. So with that in hand, we moved toward the next phase of the project, which was collecting the data. Because the data we collected from those patients at Scripps, they were absolutely cutting edge, but usually we had only very short sessions and sometimes even less than a minute. And we couldn't really test the interventions as well. And also, since the Scripps study, we evolved significantly. When we were doing the data collection at Scripps, we had just first prototypes. When we were starting data collection during this study, we actually got the first truly wireless earbuds as a part of our product as well. So actually, as we were literally, we use also the study to test one of the first truly wireless earbuds out of our manufacturer, and also improve on the user experience on the earbuds itself. So that was also incredible value that we were able to get doing that study. But the purpose of that study was that we had a cohort of 20 subjects. 10 subjects were healthy control, and second half 10 were with the hypertension stage 1. So this is the first time when we were looking at that kind of interventions, especially at the older population. The one thing I didn't mention is that was mostly older population, 40 plus. And to collect the data, we were using MindMakes brand new truly wireless earbuds that people could listen to music, could follow the breath work as well. And also simultaneously, people were using ECG strap that was also integrated with our app. So we could compare values like heart rate, heart variability, make sure that we identifying with our algorithms every heartbeat properly. And also every patient had received the blood pressure cuff to also record in our app blood pressure before and after every day, before and after breath work, breathing exercise. And also participants had the chance to use our app, which is part of MindMakes Heart Health System. We have a few different kinds of the breath work there. During the study, we focused on the resonant breathing, and I will talk about that one a little bit more as well. And the session was up to 10 minutes for each participant. We choose resonant breathing, which is a fancy word for slowing down the inhale and exhale. It's usually the frequency of the breath work is between 3 to 7 breaths per minute. We actually also been developing algorithms for each person to actually identify what is that resonant frequency. That enables to align the different respiratory rate with the vascular tones and different oscillatory patterns in our body to maximize the heart variability. So actually here you can see the snapshot from our app when the person is performing the resonant breathing. So on the top in the real time, you can see heart rate variability in real time. Then also you can see the heart rate, and also you can, as person is inhaling and exhaling, that's the gray is the pattern that person should follow. And every blue point here is actually time between the heartbeats. So this is interesting about MindMakes technology. Usually you cannot do it with the watches because they will not have enough accuracy to measure the time between the heartbeats accurately to be able to see those changes in the heart rate or between the heartbeats as we inhale and exhale. But because MindMakes has such a great accuracy, we actually can capture every heartbeat and measure those tiny differences, and based on that, see actually how our every inhale is modulating our heart rate. So actually here you can see as the person is following the inhale and exhale, also the heartbeats, the time between the heartbeats is following that pattern as well. And that's one of the important part of the biofeedback that we providing in our app, which as we're thinking about the aging population, we know that there are so many great tools like meditation, like listening to music, like a lot of different breath works as well. But always at the end of the day, people don't stick to those methods unless they see that it actually is impacting their health, their heart. So we spend a lot of time building the user experience that people can actually see that, yes, in real time, what I'm doing is helping me. So actually very often when even after a few minutes, you can see that the heart rate variability is increasing quite quickly, which is also one of the very important parameters for the heart health. We also got a lot of great feedback from the participants on that study in terms of how the breathwork was impacting their health and their well-being. Actually, we wanted to focus mostly on the blood pressure. We got a lot of great comments about improved quality of sleep and being much less anxious, being much calmer as well. So we've seen actually a lot of additional positive effects that people were experiencing using this app and those simple things that everybody can do at home or and anywhere they are. So that was part of the people could actually use that app to follow with the breathwork. And the study went as follows. So first, the first 2 days, we were training the cohort. By we, I mean really incredible team at both at UMass and with the help of our team at MindMikes. The participants were trained the first 2 days. Then the data were collected without the breathwork. Then we had a session with them with identifying what is the resonant frequency in the way that a person was doing the breathing at a different rate with increasing slowing the rate of breathing at the time when we could see that the heart rate variability was maximum, which meant that this is the most impactful, it has the most impactful, it has the best impact on the physiology. Then that frequency was then sent for the person to set in the app. And then people were doing the breathwork session for 21 days. And then we wanted to see also at the end, when people stopped breathing, could we still see the effect on heart rate or heart variability, blood pressure? Especially for us, was that systolic blood pressure was the most interesting, because that's as if you remember that first this animation, as people are aging, systole is increasing quite a lot. So we wanted to use that systolic blood pressure as a proxy to see if we can see even a small drop in the blood pressure. And every session per day was structured as follows as well. So at the beginning, that was the setup, of course. Then there were 2 measurements of the blood pressure, so we could average it out, because we also know that when people are using blood pressure cuff, there is a lot of complications with that. Then person would perform the breath work for 10 minutes, and also then at the end also, once again, a person would collect the blood pressure, because we wanted to see before and after effect. And just to mention the control session, people would just sit for 10 minutes or basically do something or do nothing. Just they were not doing the breath work. So we had that control session as well. So a little bit into the results of preliminary results of the study. So we had this controlled, so what we are looking at this plot is first we combine all of the data. This is showing the changes to the blood pressure before and after the breath work. And red is a control session. So basically people were asked they could sit, they could do nothing. But they were just asked not to do the breath work. So then in this way, we know if just, sitting for 10 minutes can also have the impact on the blood pressure, because in principle you're also relaxing a little bit. And then if you sit but you're doing the blood, you're actually doing the breath work, what would be the difference? So what we're looking at here, first result, when we combine all of the measurements, then we also separated the non-hypertensive group and also hypertensive group. And we're looking here at the systolic blood pressure. So you can actually see when people are sitting, just slow down, don't walk around, just sit and relax. This already can drop the blood pressure. But additionally, when people also do the breath work, we saw an additional improvement on the blood pressure. It's not huge. It was an average about 1.5, 1.6 millimeters of mercury. But that's the initial result for healthy and stage 1 individuals. But overall, just slowing down for even a few minutes, 10 minutes, you can already start seeing significant effects on the systolic blood pressure. And that was of interest for us because that's the best proxy toward the vascular aging. We also look at the diastolic blood pressure, and interestingly, that one is not changing that much. If you sit, if you do the breath work, it usually stays where it was. So definitely systolic blood pressure, which is we see here with those methods, those protocols, has much bigger impact. And the last one we look at as well was the pulse pressure. And here we actually seeing, when we combining those two, we see the biggest change, statistically the biggest change, because actually it means that both are actually changing. When we combine them, then we can see that the most change. So just a reminder, blood pressure is just systole minus diastole. So when we're looking at the overall change in the amplitude, which is actually the best indicator of that change in the waveform, so actually here we can see the most impact on the blood pressure. Still, that group does not include only we used stage 1 hypertension. This study really allowed us to put together the really good framework, and as a follow-up, we will be doing next study with actually people with hypertension, because now we can base our hypothesis based on that. And keep looking what are the best interventions that we could recommend to people to improve their health. And that's my last slide. This is a current MindMike's heart health system that is designed to help people to manage stress, and with the metrics like heart rate, heart variability, when people can in real time see their physiological state and learn what is calming them down, what is stressing them out. A big component of the product today is the breath work, different kind of the breath works. We especially recommended resonant breathing to help people live well with high blood pressure as well. Plus also you can see your history. And today we have the part that is you can add your blood pressure, which was very, very important during the data collection. In the future, as we're collecting more blood pressure data, our goal is actually also provide our own algorithms. So that we are in the process of improving our algorithms, collecting more data. And for what's next for us is now we'll be building a limited edition of MindMike's earbuds. Will be about 1,000 earbuds that will also give us a data set with people, patients, customers with different ages. So the study that we conducted, all of the features that we already have, once we have that database with different ages, then we will be ready to go also to build a metric about the vascular age, which when we think about user experience as well, we want to deliver the features people care about. And we do care about our vascular aging. So for us, it's also such an important aspect to, on one side, providing the doctor information that they can use to do the diagnosis, but also equally important for us is how we can build the experience that people care about, because if people care about this, then they can actually make better decisions, then they can improve their health. So that's my last slide. MindMike's system, MindMike's heart health system is already available on the App Store as well as our website. And now we will be working toward, thanks to the studies we conducted, adding further features to it as well.
Great. Thank you so much for the presentation. It was really, really interesting. We have a couple minutes for questions before we move on to the next talk. I guess while people gather their questions, maybe a quick one from me. Can you talk just a little bit more about maybe the accuracy and reliability of kind of what you're seeing compared with the catheter, and sort of what kind of brought you to the point of actually using the technology that you're using?
You mean when we're going towards the...
Yeah, so you talked more about the intervention side, and I'm kind of interested in hearing a little bit more about the reliability and the accuracy, and just sort of how this compares with other tools out there.
Yes, so I would say the parameters, so there are two aspects. One is the metrics that we're delivering today in the product, in the consumer basis, so which is heart rate and heart variability. So for those metrics, we're using the ECG, and they are in terms of the interbeat intervals. They are, we have a correlation at the level of 0.99. Even for atrial fibrillation. So even if rhythms are irregular, then we still see very high correlation. We're working now on the algorithms toward the blood pressure, because we see very high correlation in terms of the waveforms. So what we're doing now in terms of the blood pressure is about the normalization. So this is where we're now collecting a lot of data across different subjects, so we can also build the algorithms that solve the aspect of the normalization, so we can provide a good prediction of the blood pressure for everyone. So that's work in progress. We also look at atrial fibrillation. We showed that we can distinguish between AFib and regular rhythms, as well as you would do with ECG. We also look at aortic stenosis, so we see also very high correlations with those waveforms. So there is still a lot to explore, and we're doing it step by step.
Great. Okay. I see Natish raised his hand. Natish, why don't you fire?
Great, Anna, thank you so much for that, and congratulations on finishing the project and having a successful outcome. I'm curious about your thoughts on the appropriate use of technology in this context. And so I think you appropriately said that, you know, there is some data, at least, about the value of breath work or of meditation, of relaxation techniques writ large on blood pressure control. And your app, you know, in theory, or your intervention is a breathing intervention of sorts, and then in theory, you know, need not rely on technology in order to implement it. And so and this challenge, I think, we see in multiple different disciplines. And so you can either think of technology as the only route to which you get to a behavior change, or an enabler of it in a very different way. So for example, biofeedback, monitoring, outcome evaluation, something like that. And so I'm just wondering if you could comment a little bit about how we should think about that, because otherwise a cynic could say, hey, just teach people to meditate, teach people to breathe. You'll have similar effects on blood pressure. Why would you bother with this fancy technology?
I really appreciate this question. And there are two aspects to it. In terms of, we could say, like, why we would need a better way for hypertension. We have the blood pressure cuff, which is very accurate. Oh, accurate enough. It's really accurate enough, but still, hypertension is almost a pandemic. And my answer to it is, and it's my own take, is that what we're really solving is engagement and compliance and adherence. Today, we're living in the world of the TikTok and all of those things that are happening. People have to be entertained, whether it's a medical aspect or whatever it is. It has to be fun to use. Otherwise, people don't use it. So for us, actually, on one side, building the experience that is engaging and building the metrics that people care about, it's very important, because based on, if people can understand the metric, number one, this is why HRV, for example, is quite difficult, even though it's for people who understand what HRV does. It's extremely powerful metric, but people don't know how to interpret it. This is why we build that dashboard. You can see in real time where it's going. This is why also we spend time building those foundation toward the vascular aging, because we do care about aging as well. So I think to answer your question is my answer is we have to make people care with the proper user experience that is matches what people are experience that people are looking for, which is fun, which is cool, which is quick. People can see it, because only in this way we can build engagement. Otherwise, we can have great tools, very accurate, that people will not use.
Great. Why don't we take Holly's question, then we'll move on to the next presenter.
I'll make it quick. I was just curious if you could give feedback on stress itself using your heart rate variability metric, or do you need more data and is it too slow?
Oh, actually, our system with that dashboard, I didn't have the chance to spend time on that one because we focused on the looking at the vascular age, the blood pressure. Indeed, our system already is trained that when people are using it for a few minutes, when you collect enough values of the heart rate and heart variability, it already has a personal baseline. And then in real time can show if you're going to fight and flight or rest and digest. And it's literally real time system when you can see how your body is responding.
Great. Thank you.
Great. Why don't we move on to Edward's presentation? There is a question in the chat if you want to go ahead and answer that for everyone else's benefit. I think that would be helpful. And so our second presenter today is Dr. Edward Wang, who's an assistant professor at UCSD in San Diego, and is also the founder and CEO of Billion Labs. He's also a year one project awardee from Mass AITC, recently completed his project, and we're looking forward to hearing the results that he's talking about today.
All righty, let's do it. Well, thanks for the shout out on we need to improve our blood pressure monitor, because that sets me up for my conversation to you all. So thanks for the intro, Julie. So my name is Edward, and I'm an assistant professor at UCSD, and also through the work that we did in grant year one, we actually formed a company called Billion Labs. I formed it with my student. I'm the CEO of the company, and he's taking a leave and working full time on it, and the company is called Billion Labs. So today I'll talk to you both about what we've done in the grant year one technology and how that taught us about shortcomings of technology, how to improve that, and then how we've sort of taken that on, and then subsequently we're also at grant year three, and then I'll also tell you a little bit more about that. So with that, let me go ahead and get started, and the cheeky title will make sense in a bit. But what we're talking about today is a smartphone-based blood pressure monitoring that is only a buzz away. All right, so my lab at UCSD, called Digital Health Technologies Lab, one of our main focus is really around this idea of developing remote health monitoring that is fairly elevates access through the use of technologies. And what kinds of technologies are we really looking at is this idea of mobile technologies that are mass produced. And what we want to do is leverage that mass production of these devices to drive the cost down ultimately. And through that mechanism, drive the adoption up. And as we've seen in both what I'm going to talk about and also what the previous talk is about, is really these kinds of technologies. They're pretty fancy. They have a lot of very impressive sensing technologies that would have otherwise cost a heck of a lot more if it's not because of mass production. And so the ability to just sort of leverage that is really where we're sort of hinging on. And so smartphones is really what I'm talking about today. And in particular, smartphones is one of these technologies I've really seen that adoption. And I've given this style of a talk, a number of years, and every year I think that this point is just made for me. And here it's kind of funny. My first time giving this talk, I was maybe here, and now we're here, and so before, I think I might have had to be a little bit more sort of well, older adults, their adoption is not as high. Well, now I think even that's getting closer and closer. So I think I didn't put it up here, but the average American, I think it was 74% of all adults above 18 own a smartphone. And when we sort of look at that, and this is not even the most up to date anymore, But in 2021, those above 65 were at 61% adoption. And so I certainly need to go find the more updated version, but it seems like every year it changes. So I have to update my slides more frequently. But my point is simply that smartphone adoption is very, very penetrated, and we can leverage that technology to bring health monitoring capabilities through to individuals. And so the goal of my research at UCSD has been around this idea of transforming the billions of smartphones in the world, in everyone's pocket, into health monitors. And by that, I mean turn it into a blood pressure monitor, into dynamometers, spirometers, and more. Today, what I'm going to talk about is blood pressure monitor. I won't talk about everything. I'll talk about blood pressure monitors. And so the technology that I'm going to talk to you about is funded through Mass AITC's grant year 1, and then subsequently we're now working on the grant year 3 work. And so the technology came from UC San Diego, and then now it's at Billion Labs, which is the company that I've formed. So what are we talking about? What we are talking about is using a smartphone, and what you do is you press your finger down, and as you're pressing your finger down, what we're basically recreating is the same concept of a blood pressure monitor, that you're applying pressure onto the artery. And I'll talk about how exactly this works. But essentially, imagine you're pressing your finger to increase that pressure, and then we'll measure how that changes the arterial response. Without internet, without user calibration, we're able to then convert that measurement into a blood pressure measurement for both systolic and diastolic. Why do we care? So hypertension as a silent killer is really this, as I guess it's kind of nice to actually come after someone's talk. So I don't really need to go into it in too much detail, but really what we want to be able to touch on and to be able to address is the idea of early screening of hypertension. And the reason for that is to allow for appropriate behavioral and dietary interventions like the one we saw just now. And if it's too late, further into the later stages, pharmaceutical interventions to be able to prevent things like strokes, vision loss, heart failure, and heart attacks. And so our particular goal that I'm going to talk about is really this idea of highly distributable early screening of hypertension. And to make that happen, before I sort of go into the details how we make it work, I want to talk about sort of this idea of calibration for blood pressure monitors. And so if you walk away with anything today, we can learn about calibrations. And so there's this sort of idea in blood pressure monitoring world where there's this need for calibrating. And so calibrating, what we're really talking about is calibrating to a user. So when we perform a measurement to measure your blood pressure, if we need to calibrate it, what it means is that we need to use a device to measure your blood pressure to then calibrate the measurement that we are providing for what is your blood pressure. And so your blood pressure monitor that you might have access to or in the hospital is what's called a calibrationless approach. And so what that means is that device doesn't need another device to help it calibrate. It can measure blood pressure by simply measuring your blood pressure. If you buy a blood pressure monitor, you don't need to go and find something else to like calibrate it. You just use it and then it will measure your blood pressure. And so that works for both a cuff-based system where it applies pressure, but also if you were to catheterize directly right into the artery, you measure the pressure directly in the arterial line. Now there's sort of this other world, and slowly I think it's sort of creeping into the general public's knowledge as this idea of calibration needed techniques. And so every time I talk people about blood pressure measurement, they're like, can't the Apple Watch already measure blood pressure? Well, first of all, no, it cannot. But what people are thinking about is these ideas people have talked about, which is to measure this sort of secondary measurement that is correlated with blood pressure. So there's two main techniques that people have leaned on. One is called pulse transit time, and basically looks at the time in which the pulse traverses a arterial tree. And so basically imagine you have a pipe, right? And then your heart beats. And then that ejection of pressure will create a wave that comes down the arm. And so to simplify it even further, the idea is basically at higher pressure, that traversal is faster. And so the amount of time it takes for the pulse to reach your finger, let's say, is faster or shorter amount of time. And so the pulse transit time decreases as you have higher blood pressure. And so pulse transit time is one of such measurements where people have looked at, which is highly correlated with blood pressure, but it requires calibration. Why? Because your arm is different size, your arterial stiffness is different. And so without calibrating, at least nobody has solved it without performing a calibration. A second measurement is what's called pulse wave analysis. Pulse wave analysis is perhaps the more, I think, attractive technique that people have started really working on. And I think perhaps is why people have talked about the idea that the watch could potentially do this. And what it looks at is a sort of slight variant of the problem, which is essentially your pulse comes out to your finger. But then that is not the only wave that comes down your finger. Another wave is actually one in which I usually like to do this when standing up, but basically it comes down through the body and then it reflects. And so that second reflection, I think, and I had this beautiful animation earlier. I'm going to have to ask you for that one. It's super nice. Basically, the reflection comes, and what you have is this sort of addition. And you basically, if you stare at these pulses long enough, everything looks like a pulse. But basically, there's this sort of initial pulse wave and then a secondary bump. And that's actually the addition of these two reflections. And so at higher blood pressure, that reflection comes faster and stronger. And so then it becomes this sort of change in shape of that pulse. And so what people have looked at is using that measurement, optically measured at the wrist, and calibrate that to your personal sort of arterial stiffnesses and body shapes and so on and so forth. Now, those techniques, if they work, that's awesome. The problem is that they need to be calibrated. And so for the particular problem that we really want to address, what we're interested in is to be able to perform screening for those who are not even thinking to measure their blood pressure, right? If they're not even thinking to measure their blood pressure, they're certainly not going to have a blood pressure laying around trying to calibrate this really cool system that can perform continuous blood pressure measurements. They need access to a blood pressure measurement. And so our goal is really to be able to create a solution that is calibrationless or calibration-free, such that we don't need a blood pressure monitor to calibrate our system. We are the calibrationless measurement. Now, I spent all this time talking about it. Now let's talk a little bit more about how this works. So calibrationless blood pressure monitoring, a most common solution to this is what's called oscillometry. And that is how the automated blood pressure cuff works. The automated blood pressure cuff, to perform a measurement, essentially applies pressure. And by applying pressure, what it's trying to figure out in a simple way is to look at how the artery gets collapsed, both because of an arterial stiffness, but also because of the pressure that it's inflated by. And so the details of which requires a lot more description. So I'm just going to describe it sort of qualitatively. So what you see here is a blood pressure measurement as this is actually how the cuff works. So it inflates all the way up and then it lets down, right? So it releases pressure. As it releases pressure, what happens is as systolic blood pressure, once it reaches systolic blood pressure, the pulse starts coming through. And this is a little bit trickier to explain, but what ends up happening is at mean blood pressure, there's this sort of reversal of trends and basically creates this shape like this. And then once it reaches diastolic, it evens out again. And so what you get, this is a measurement straight from our app, is at a lower blood pressure, that peak at mean diastolic or mean blood pressure is at a lower pressure. And as your blood pressure increases, or as a person's blood pressure is higher, you get this shift in this peak. And this is the very basic concept of oscillometry measurements. So what do you need to perform this, right? What you need is, one, you need to measure the pressure that you're applying. Not crazy. You need to measure the pressure. The second is you need to measure the pulse amplitude. Right? So you need to measure how strong is it coming through. So you need to measure how hard are you pressing, or how hard are you applying pressure, and how strong is that pulse coming through. And finally, you need to use that two measurement, combine that, and then compute the systolic and the diastolic blood pressure. So here comes our actual problem. Well, what did we actually do? Right. And so what we proposed in our first year in grant year one was we had this kind of a cool thought, kind of crazy thought, was what if we can perform this measurement without modifying the phone at all, but you creating this very, very low cost physical attachment that goes over the phone that can convert the smartphone camera into a pressure measurement system. I'll tell you about that first. And then through science and magic, I guess, we came up with a new way to perform this whole measurement with no attachment through actually much of the learnings that we got through grant year one. And so our first approach at this came out of the came from our research lab where we thought maybe what we could do to allow the phone to measure both the pulse and the pressure is by creating a little attachment that goes over the camera. And the goal is really to create something that is less than $1, something that's, I've always sort of said this is cheaper than a pack of floss, and you can just give it away at, you know, like toothbrushes are at what do you call them? Dentists. Man, I haven't given this pitch in a while. But the idea is really it's so cheap that everyone can have it. You can provide it to anyone who needs it. And all it really took is to make an attachment that uses a spring. A spring, much like how a finger trainer works. You know, those who don't know, a finger trainer is basically a spring-loaded device where you press down, and as you press down, because there's a spring, as you press down harder, the resistance goes up, right? And so you can essentially create a little device that as you press down on it, increases the pressure that it is applying onto the finger. And so with that concept in mind, we set out to build a little device that augments the phone's camera in this way. So there's two holes, essentially. One that takes in the flash of the camera. This is the back camera. So there's a flash. It lights up, goes through this channel, it lights up your finger. And every time your heart beats, a little bit of blood comes into your finger, comes in like this. And so the light that reflects back from the camera, or sorry, from your finger into the camera will basically pulse like this, right? On top of that, what do we do? How do we get that measurement, right? We get this measurement by another hole that comes from the finger and then goes back down to the camera. And so with that, what you get is basically this little pinhole projection that goes onto the camera. And what you do, as you press your finger down, the spring loads, applies pressure on your finger, increases that pressure that's applied onto the digital artery. And not only that, now we've sort of created this little pressure sensor transducer, essentially, where as it gets more pressure, it's also closer to the camera and you get a bigger circle. And so by measuring the size of the circle, we can measure the pressure that is being applied to the finger. And so with a very simple attachment that uses a spring, we were able to convert a smartphone camera into a pressure transducer. We combine that concept with what I just talked about, which is every time your heart beats, blood comes into your finger, and I can measure that through the brightness. And so if there's no blood coming through, it'll be a constant brightness. If there's a bigger pulse coming through, I'll get a bigger amplitude, right? What that looks like, this is a raw-ish data that came off of a measurement on the phone, is like this. The red is the force that we're measuring, so basically the size of the circle. As the size of the circle increases, we're measuring the pulse, right? So the pulse the brightness coming off of the camera. And you can see that exact measurement that I talked about before, which is the pulse, as you reaches diastolic, it increases to mean diastolic, or mean blood pressure, and then it gets cut off. So with that, what we had done in grant year one is we recruited 29 people. We ultimately had 24 usable measurements. And we had a range of blood pressures and a range of skin tones, which are not on here. And what we were able to do is get honestly pretty good results for our systolic and diastolic blood pressure. And remind you, this is what we call no calibration at all. This is just straight our attachment onto a camera, and you follow it on screen guide, and you basically just slowly press your finger down, right? And so what we have here is for systolic, what we have is a correlation of 0.75, a diastolic for 0.66, and then a mean absolute error of 8.7, and then a mean absolute error of 5.5. What that translates to, it's a little hard to sort of describe that, but I think the easiest way is sort of, let's just look at the plot, right? And so what we're really able to do is if your blood pressure is above 130, we are able to sort of actually see that your blood pressure is high, your blood pressure is low. And that's really kind of the point, right? Our goal is to do screening. Our goal is to be able to provide something so cheap that you have no idea what your blood pressure is, let's measure it, right? We don't need to worry about the cost, we just get it to you. And I think what we've been able to do through this is that the concept of measuring your blood pressure through your finger with this like sort of low cost solution is viable. But as with all great inventions, there's limitations, and we found lots of them. So the first thing, and this is sort of the beauty, I think, of having focused on older adults as a starting point for our work, is turns out it's actually really hard to press smoothly on this clip. And so we tried a bunch of things, and there was some solution to this, which is if you were really attentive and you sort of stared at this plot, you'll notice that we don't actually have people press smoothly. What we had people do is actually they press at different levels. So basically we had this little guy that asked people to press and press and press and press and press. The reason for that is you can't see the clip. It actually sort of sits behind the phone like this. And so turns out without proprioception, it's really difficult to control your finger in this really smooth way. And so it was easier to get people to hold at different levels, which then turned out it takes really long to do this measurement, because for you to hold at each level, it ends up taking about like 2 to 3 minutes or so, which is one problem. The other problem is that it's simply difficult to, if you ever try, well, it's hard to try without my little device, but it's actually not super hard if you were to press on a flat surface and just try to apply more pressure. That's pretty easy. But to move a device like this and slowly increasing pressure turned out to be really difficult. And so we learned that sort of through working on this, having gotten both the performance, but also human factors. We really focus on the human factors when we're working with different people, especially older adults. We learn a lot. On top of that, as we started really staring at the manufacturability beyond sort of that small batch, it was very hard to actually scale up at a cost point of what we wanted. And on top of that, trying to actually package things, get the spring consistent enough across different batches, that just turned out really difficult. And so those were our learnings, but that's not the end of my talk. And so through what we learned and sort of the challenges of how to press, what we learned is you can measure blood pressure from the finger by pressing down on it. But having attachment makes it really hard for it to be a viable actually product. And having something that moves turned out to be really difficult to use. Around the same time in my lab, we came up with this kind of a crazy measurement where if you vibrate the phone, you can use that same vibration to measure the pressure you're applying to the finger. So with that, we came up with a software approach that we had then proposed for grant year 3, and subsequently we had licensed this technology directly to a startup company with my student that we formed to develop this further. And so that's why I will end today's talk on, which is our second approach, try again, where we came up with this thing called vibrometric force estimation, where when you vibrate the phone and you press on the phone, what it ends up creating is this interesting phenomenon where you have a vibration motor. And so the top graph there is basically, imagine your phone is just vibrating, and that vibration is constant. And you apply pressure, increasing pressure. By doing that, what ends up happening is you essentially dampen that vibration as you press harder. You can sort of think of this as you're basically clamping the end of a vibration, and then it basically changes that vibration. Easier to think about it as the harder you press, the more it dampens that vibration. How do we measure that? There's a convenient sensor on your phone called an IMU, which is an inertial measurement unit. Essentially, it's an accelerometer and a gyroscope. And we can use that sensor and measure how the vibration changed. And we train a model for different phones. So you can imagine different phones have different vibration motors, different structures, different sort of casing, so on and so forth. And so what you have to do is actually you tune a model per type of phone. You don't need to do this for any one's personal phone. If you have a Pixel 8, I've tuned it. It works on any Pixel 8s. If you have an iPhone 14, I've tuned it on iPhone 14, then it's tuned, it'll work. If you have a, I don't know, Xiaomi 725, I don't know what it is, and I haven't tuned it for that, then it probably won't work. But the idea is that we can introduce a new phone through a very simple what we call in-factory tests. Basically, we do a very simple calibration procedure to measure that vibration to force relationship, and we're able to quickly tune our force measurement technique to different phones. So here we show 3 different phones where we successfully tune that force measurement model onto the phone through programmatically. And so here's 3 different Android phones, totally different makes, different years, different price points, and we were able to make it work on all of them. All they need is a vibration motor and an IMU, which nowadays every phone has it. And so to sort of visualize that just a little bit more, what we're able to do is measure the applied pressure using this technique where we vibrate the phone and measure the vibration change. And on top of that, we place the finger on the front camera. So imagine the phone's basically laying on the table. You put your finger on the front camera and you press, right? And by doing that, the camera, again, is acting as a pulse measurement, and it measures the pulse size change by using the optics. The size of the pulse is measured by the oscillation amplitude. And so we're able to now capture, again, applied pressure and the pulse size. Combining the two, again, we get the same idea of this oscillometric measurement. We get that peak shifting as your blood pressure increases. And so we've ran a feasibility finding study. We have multiple studies planned for grant year 3. This is the feasibility finding we've done, where we have people change their blood pressure by performing a isometric exercise. Isometric exercises are basically like wall sits or a banded leg lift. That increases your blood pressure. That allows us to perform a study where people's blood pressure is perturbed. For the grant year 3, what we're doing now is performing a study with natural blood pressure variation. So people with actually naturally high blood pressure. So that's what we're working on now. But our initial results are pretty heartening. It's not perfect, but I think it shows that we're pretty close to replicating what we had before, and our hopes is to now be able to do exactly what we showed before, with the problem of the usability, I don't know, solved, but better, without having to move your finger because the phone is still. And so now we remove this need to translate your finger to increase force and pressure, while not having any hardware. And then so finally, what we're doing now is really trying to push it beyond sort of this prototype. So it turns out it's still not very easy to do this, and we really need to get people to know what they're doing, how to use it. So we've been able to through the support of Grant Year 3, we're now we have a designer working with us, really improving our visuals, working with older adults, and doing studies, more studies, always more studies. And finally, I think I'm out of time, so I always want to thank both my lab and the company. Everyone's works very hard. So thank you. I will take any questions.
Thank you. That was really, really interesting. I think we're out of time, but what I loved about the 2 talks is really kind of thinking through the limitations and kind of how you've learned. Maybe Deepak, if you have one quick question, then we wrap up.
Sure, but thank you both. Great talks. Yeah, Edward, I can ask, spend a lot of time in questions, but just very briefly, I think maybe there is, phone casing maybe has causes some calibration issues for your vibration sensor. So I'm assuming you'll have
Yeah,
to
we ask people to
deal-
take their phone off.
you have to deal with that.
We have a
with that.
screen that says, please take your phone case off.
Yeah. And the other question is, I'm curious, what is the, is there a limit on the minimum amount of time you need to measure? Because I noticed that the previous round was 100 seconds. I'm curious if you've tried
Yeah,
throttling that
it's
back.
our
What's
test
the
now is
limit?
40. Our test now is 40 seconds. So it's basically it's much more similar to how a blood pressure monitor works now. And so it doesn't take into account like the turning on the app and then like putting it on the table and then clicking through the prompts and then putting your finger on there. But once you start the measurement, right now we have a 40-second measurement. It's to make sure you get enough pulses. We haven't really tested changing that, significantly, like making it way shorter. I'm not sure if it, I mean, you're basically, it comes at the cost of how many measurements of a pulse you get.
Right.
I think it's
just
possible,
curious,
but yeah, it's not, it will never be instant, I think is one way to say it. It'll never be
right. I'm
instant.
just curious how much they can tolerate, how much of constant pressing an older adult can tolerate before the pressure releases. But yes,
Yeah.
40 seconds seems reasonable. Yeah.
Yeah, I think 40 seconds seems okay. Yeah, I think it seems okay.
Great, thanks.
Amazing. Well, thank you all for joining us. Two really interesting talks. And I saw they both provided their contact information throughout. And just to highlight what David pulled up is that there is another webinar that we're hosting in July, and look forward to having as many of you there as possible. Thank you.